As a part of the IGNET project, the efficient and lean C++ program dense_NN was installed and used on a Windows computer to train dense-type deep learning structures. This video described how dense_NN can be used on a Linux system. To do this, dense_NN is installed on a Raspberry Pi 5 and the training of a deep learning structure is again demonstrated using the MNIST dataset as an example. To get started with this topic, I recommend the video Training Dense Networks with the C++ IGNET project. I will describe the installation of dense_NN in some details and of course provide an overview of the entire training workflow. So welcome to the video Deep Learning Structures with dense_NN on the Raspberry Pi 5. I would like to start with a brief overview of the Raspberry Pi 5 workflow. In line with the IGNET concept, data preparation is carried out on the desktop or similar device and are transferred to the Raspberry Pi 5 in this example. The C++ program dense_NN is installed on this system. It is clear that the Pi 5 can just as easily be an HPC system. Training is performed on the Pi 5 and the deep learning configuration and training log are transferred back to the desktop for evaluation. I will start the dense_NN installation on the Pi. The src and include directories must be created on the Pi as shown here. The description of the dense_NN installation is stored in the cmake_list file. I will discuss cmake_list later. The src directory contains the cpp files of the dense_NN src directory, and the include directory contains the header files of the dense_NN include directory. Now let's move on the cmake_list text file. cmake_list is the roadmap for installing dense_NN. It is important to enter C++ standard 20 here, otherwise essential components of dense_NN will not work. Here are the cpp files to be used and here is the roadmap in detail. The cmake command reads the roadmap and use it to generate all internal structures. Include the cmake directory, which I forgot to delete for this demo. Make then only execute what cmake has prepared. I perform the installation via remote shell on the Pi by changing to the desired directory. Then creating the build directory and changing to that directory. And calling make as shown here. That was the first part, and dense_NN is created with make, taking into account the 4 cores of the Pi. After a short moment, the executable dense_NN program was created. I checked this by changing to the newly created build directory, and I'm happy to see that the file is here. For a better overview, I copy dense_NN from the build directory to the ML directory. And the training data via FTP from my desktop to the ML directory of the Pi. This takes a few seconds. And here it is. Now all the requirements for demonstrating the first training session have been met. In this training session, RMSProp is used as the optimizer and the training is performed on the Pi via remote shell. The training is performed for more than 109,000 parameters and takes more or less 10 seconds per epoch on the Pi. After about 25 minutes, the training is completed with a less than satisfying quality. I will take a closer look at this by downloading the parameter file and training log to my desktop and visualizing them using the R script display training progress Pi5. To do this, I need the R package JSON lit. I load the two files mentioned above and run the script. The visual expression shows very clearly that the training did not proceed as expected. The video shown above demonstrates that there is room for improvement. Let's see if the training with the SGD optimizer goes better. I change the parameter to SGD optimizer and restart the training. The training only takes about 13 minutes and is completed with significantly better quality. Here, too, I display the training progress graphically, download the parameter file and network configuration again, and run the R script. This looks much better and meets my expectation. However, I don't want to discuss possible challenges regarding the RMSProp optimizer at this point, as this video is primarily about installing DenseNN on a Linux system. This brings me to the end of the video. I'm pleased to have been able to show that the efficient and lean C++ program DenseNN can also be installed under Linux and that DenseNN can be used on a system with limited resources such as a Raspberry Pi 5. It is clear that the Pi 5 can be replaced by an HPC system in this workflow. But of course, DenseNN together with the Pi 5 can play an interesting role in an edge computing system. I would be delighted if you tried out DenseNN and gave me your feedback. See you next time.